de lo que va a entrar para este jueves. Así que veamos la tarea. Y después vemos otras preguntas de otra cosa, de otros temas. Déjenme compartir esta pantalla. Acá. Entonces, acá estoy. Debieran empezar a ver la tarea. Esta es la tarea que ustedes tenían, ¿ya? Vamos a grabar esto así como... vamos a grabar una copia para no pisarla. Y la vamos a poner... No me acuerdo cómo le estamos poniendo. Entonces, básicamente, aquí se les decía... Ok, perdón, voy a pasar a inglés por respeto al curso. Y igual si tienen preguntas en castellano, las pueden tirar en castellano, no hay problema. Okay, so let's review the homework so that you know what you had to do. Basically, you had a velocity field, which was very simple, just proportional to the location, right? And maybe you did, but you can check that actually this velocity field is conservative. The conservation equation holds true if you analyze this. And you were given a grid. So basically, you have a delta x, a delta y, which are just the same, and over a grid between 0 and 3, you computed the velocity field. This function just creates a mesh. So instead of having a vector, you have an array, a matrix with x and y. So just so you see, x is a matrix of 31 by 31, and all of these velocity components should have the same shape, right? And this is just a function that plots streamlines directly. So you just give it the vector coordinates, and you just give it the velocity, and you can paint it by the magnitude. And we are interested in, you're being asked, okay, what's the streamline that passes through this point, 3,1, right? And you had to do this in two ways: one analytical one and one numerical one. So you should know that in order for to define analytically a streamline, you need that the ds vector cross, I think it is. No, well, the ds vector cross b has to be 0. There is a there is prot maybe. Anyway, so the cross product has to be 0, right? And we've done this in class. Maybe you can review it, but basically you end up with a function x times y equals some constant. Oh. Okay. Yeah. So all the streamlines look like this. X times y has to be a constant, right? Because dx over u has to be equal to dy over v, right? We did this in class, and it's actually one of the examples on the book. So this should be more or less simple. And the only thing is that you need to find this k, this constant, for the streamline that you're analyzing. And since you're giving the point, basically what you do is that the constant for your streamline is just x0 times y0. And then your y's are just k0 divided by x and the vector x that you're being given. If you run this, this should be it, right? You can explain it in more detail, but that was it. Is this clear, or is not clear enough? I'm gonna assume it was clear. And if you do that, and then you plot it here, you should see the streamline going through, yeah, just over the streamlines. Okay, so that was the analytical part, more or less straightforward. But you need to know that the equation is that your ds has to be parallel to the velocity field. Okay, so there you got your 5 points, and then you were given the task to compute this numerically. Okay, I received a couple of questions, and we talked about this last recitation, and I gave you a little hint that you had this function that interpolates. This basically these two are functions that interpolate your your velocities, right? So you're given the space where u and v are computed. You're given the point where this of the point, I mean the coordinates of the point where this streamline has to pass, and you have another parameter which is the delta t. Okay, so you're being given a hint. There are many ways to do this, but basically the main idea here, and let me just I'm gonna keep with the LaTeX, I'm sorry, but basically the main idea here is that the new position of your point. Oh, this should be text. Sorry. So the new position is going to be your old position plus delta t times the velocity times u. Okay, and this is a first order approximation. This is just an approximation. You know, you can work out the math, but basically this comes because x new minus x old divided by delta t is more or less the velocity, right? Or you can think of it as if you have a point and you know the velocity, you know that over a small period of time, you will be moving with the velocity. So as long as delta t is small, then your new position is just in the same direction that the velocity. And this, of course, has an error, right? Epsilon. Oh, epsilon. And this epsilon is, we call it big O delta t. Right, so you're making an error which is similar to delta t. Okay, so as long as delta t is small, then you should be fine. You should know this from calculus, and there are many numerical methods to do this better than this. But this is really a basic one, and I think everyone should have known this. Did all of you knew this, or is this a surprise for you?
Professor,
Yes.
in the one I sent,
Yeah.
explained the procedure like with the same equation, but at the time that I was programming, I had more difficulties and the result didn't come out. But if I explain it same as you did, do I have points? I don't know.
You may get a few points. Yes. Yes. Of course, not full points, but some. If you know, sometimes you have the idea, but you don't achieve to write it how it was in your head. So you get a few points. but of course not full points. Because, like I said, this is really easy, but how you code it is can be tricky, and there are many ways to do it. So there is no one right way. So here I'm just going to show what I would have done. So basically, we're going to be storing several values of xj, and the first value is going to be just x0, right? The same with y, x0, x0. That's one way to do it. And then we need to know the velocity at that point.
But
Sorry,
sir,
this is y.
the y0.
Yeah, thanks. And we need the velocity. And the velocity at that point is just going to be u inter the x0, y0, right? And same with v. Now this is a bit, and just to show you, and then the next point, let me just show you, the next point is going to be x0 plus delta t times u, and y0 plus t times v. So this is pretty straightforward, but the thing is that you want this to be done, automatically many times. So in how you automate this, there are many ways to do it, and that's actually the tricky part. So what I would do is I would say, okay, xj dot append. I saw many of you know how to use this. So with append, you just put this at the end of the list. But then this x0 is not always the same. So it really should be the last item on xy, right? So that you do this with this index with -1. This is one way you could have done it differently. And also this value, I'm sorry, this is y. And also this value should be done over the last one. So xj -1, ij, yj -1, right? And this should be done here. Okay, this looks okay. But you need to iterate this. So you could do just a very simple thing, do it 10 times. If you don't, because you don't actually know how many times you need for this to work, right? And this should work, I think. So if you just test it, he just plots it for you. There you go. But you didn't. Let me just do this.
Sir, relate the for method with the dt, like 10 divided dt times
Yeah.
the iteration.
Yeah, like I said, there's many ways you can do this. One could be, what did you propose? Okay, here.
Or I in range
Yeah.
int of 10 divided by dt.
Okay, this is still arbitrary, you see?
But
it
the
doesn't-
range for
Yeah,
I.
yeah, you're right. But this is still arbitrary. I mean, it's always going to be arbitrary. And this is where most numerical methods spend their time. Because you see, here we're not plotting it, but this, I don't know where it finished, So this and you can see that we're deviating a bit. So what should we do to get a better approximation?
To put
If we
a small dt.
Yeah, smaller dt. So let's say 0.05. Then we get closer, but it's not nice enough yet, right? Now we're talking. Okay, so this is one. I just want to say this is one way. Okay, there were many ways. Normally, you would, yeah, you can also, you could have done something like x old equal x0, and then x new. You compute it and you iterate over that. There are many ways. As long as you're doing, this is the critical step. This part here. If you're doing this right, then it's okay. Also, you could have done, while I don't know, AJ. This is what I actually use, and it's not the nicest. It's smaller than I dot max. This is what I use, but again, oh, what happened? It's not the nicest, and it doesn't always work. Oh, I have an error. Yeah. So in that way, you don't need to guess how many steps you need. All right. So anyway you did it, as long as you have this step or something like this. This is the critical step, or something like this. I mean, you you could have done this, more detail in a Runge Kutta scheme or something like that. That would have been fine too. Somebody's saying we could use backwards Euler. Yeah. Again, I don't mind what numerical method you use as long as you know what you're doing. Okay, so the main point is that realize, because we didn't talk about this in class, the streamline is nothing more than when under a steady state is the same as a path line. So if you integrate the position of a particle for whatever method you want, then you get good results. Okay. I'm sorry, I skipped a couple of chat messages. Okay, people had problem user uinter and vinter. Okay, but again, guys, fellows, friends, you can do this and you can see how it works. You can play with this kind of things. This is everything is open source, so you can look how it works. So you can try things outside the function, and then when you're happy to just put it in, right? So, and I never got any question with the uinter and vinter. We did a couple of sessions with questions, and you can send me emails. So yeah, this shouldn't be a problem. Anyway, so this is how it was done. So okay, here we achieve a nice result with this time step, right? And realize, maybe it's not obvious, but realize that you're computing on time, but showing your results on space, right? Because you're actually plotting on space, but basically you know that it takes a while to move from here to here, and that's the domain you're actually computing stuff. Okay. And then you're given a real flow. Of course, this is not a real flow. I created this data. You can just load it, and here we upload. I'm gonna copy this because it looks better. So I'm gonna create a larger plot. So this is a very messy plot. It looks like you have flow in this direction that goes up a chimney or something like that. You have here something that is blocking the flow. So it's pretty irregular. So the idea was that in this case, you cannot have a definition of a streamline. We've been working on this analytical framework in which you need a description of the velocities. You need a function of u and v. And here we don't have a function, which is the case for many fluids. We don't have a function. You might have data, or you might have results from a numerical model. So you need to be able to integrate the streamline or whatever other property. So in this case, many people said, well, but I don't have anything to do. I just use my previously defined function. It might be, I don't know. When I did this, I couldn't use my function in the two scenarios, because I just wrote it too specific for the previous problem. So you see, in this case, I'm using, what is it? 0, 1 as a time step. And it looks more or less like the streamlines, not very, very good. Actually, I want to show you something because I realize oh, it ran. If I run with 0, 1, I get this not very nice behavior. And what happens if I use an even larger time step? Well, maybe you can't see. It took me a while, but what's happening there is that it's stuck into a loop, because you recall that I just put this condition to break, and with a very large time step, the streamline doesn't go up, so this condition never happens. So maybe if I use this one as we did before, then it should run with a very large time step. Yeah. Then we can plot it. It should be rubbish, just rubbish, right? So let me just to nice things up. Let me just return this here because I think it's not a bad condition. And the question was, okay, the value, right, of at the top. So let me just use a more reasonable time step, similar than before. Run this stuff. It looks more or less okay, right? I think it was 0, 0, 1 before. Yeah. It goes more or less into the streamline. So you can I think it's IN. I think it's yeah, IN. So yeah, but the question was XN, right? So here you just need, oh, this is very messy. You just need to find X when Y is 5, right? But it's something like 4.8 or so. Okay, so far, was this clear? I can assume it was. Oh, anyway, now the bonus. The bonus was, how can you improve the accuracy? Of course, you're absolutely right. You can use a better numerical method. That's right. But here you were given a hint. Use the acceleration, because as we talked before, let me just copy that from before. This guy over here. So one way is to use a better numerical method. Another way is using better math, right? So you could, let me just, I'm gonna write this a bit differently. So it's just here, the previous step times the velocity times delta t, and you can add this, the acceleration times delta t. In this case, it has to go square, right? As a certain epsilon, and this actually had to
Also
be
divided by
divided by
2.
2. Sorry?
Divided by 2.
Yeah. Right. Let me just delete this so it looks nicer. Okay, and in this case, the error is delta t squared. So your numerical method is way better. It converges more rapidly, is better, right? This could have been more or less, again, straightforward. This is just physics. So you should know, or you could have known this easily. The tricky part is to actually compute the acceleration, right? So in order to do that, can you can you s- can you see my screen? Can you see this equation?
Yes, yes.
Yeah. So what you had to do is that you had to remember this bit, right? Uh, Even though, and this is important, even though we are in steady state, we still have acceleration because the velocity field is changing. So as a particle moves, the velocity is changing, and therefore it feels acceleration, even though we have steady state, right? So the velocity is not changing over time, but as you move through the velocity field, you're feeling that the velocity is changing, and that's by definition acceleration. We call this convective or advective acceleration, right? And in our case, is only these couple of terms for x and this couple of terms for y. This is clear for everyone because this part is fluid mechanics. It's actually just fluid mechanics. So this is 0 because it's steady state. This is steady state. We don't have set vertical velocity. So only these guys, right? So this is fluid mechanics. And the thing is, okay, how do we, in order to incorporate the acceleration, we have to actually compute it. Okay, and that was where you earn your bonus. So we're gonna compute the acceleration field based on x, y, u, and v. Again, there are many ways you can do this. So if you did it one way or another, it doesn't really matter. But I'm gonna do it the way I find it more easy. So what we need is we need du over dx here. We need du over dy. Then later I'm just gonna write that down. We need dv over dx. We need dv over dy. Let's say we have those. And then we're gonna say, okay, the acceleration on x is gonna be u, whatever u we have, times du over dx plus v times du over dy, right? This bit. And then the acceleration on y is going to be u, but dv over dx and v dv over dy. We return these two guys. This is the core. Of course, the details matter. They say the devil is in the details. Have you heard that? So yeah, this is the core, but how you do it is actually can be tricky. The thing that you need to realize is that if you take the difference, basically this all of this, for instance, U is a matrix, right? So you can see U, and what we are interested is in the difference of a long x and a long y. So basically, you can compute this derivative as just the difference between one value and the one to the left divided by the difference in x of one value minus one to the left. And the same in y. You know, this is, maybe you can't see it clearly here, but u is the horizontal axis, this 31 horizontal are on x, and the 31 on the vertical are on y. So one way to do this, there are many ways. You could do something like, well, the most direct way would have been to say, okay, x in all of the y's, and then from the not the first, you know, in Python the first one is the 0, right? So one on is actually from the second on minus u all of y's. Here we have we want them from the beginning up until one before the last one. So this is just a difference in u. This divided on the same thing on the x matrix. So on all of the y's, 1 onward minus x, all of the y up until the last one. And in y is a bit different. We want, okay, from 1 onwards on y and all of the x minus 1 from the beginning up until the last one, just one before the last one, and then all of the x. And the same on, this is y in this case. So y, 1 onward, all of the x, minus 1. Okay. And you can easily show that this is the same for v, but you only need to change this one.
Sir, can you zoom in a bit your
Oh,
screen?
yeah, sure. There?
Perfect. Yes. Thank you.
Sorry. Okay, this is one way. Okay. What I did is a bit different, but it's the same, so it shouldn't matter. Oh, what's what I did? Well, doesn't matter. But you need to realize the following: that this matrix is going to have a different unit than u. So if you try to do this, you're gonna, okay, it is running, but if you try to compute this thing, just call it ax, ay, and we're gonna use the previous velocities. There is an error here because u and these guys have different units. So we need to select u only in the values that we really want. So again, there are many ways. You can just select the initial one, or you can have an average. That's also a possibility, because you're subtracting 2 on the x. So I'm gonna just stick with the first one. So it's gonna be all of the y's, and then I'm gonna select from the first one. It shouldn't change much. And on y, I'm gonna do the same. All of the x. And this should be the same here. Now this should run. Oh, okay, I made a mistake. Oh, yeah. I'm sorry. So the problem is here. Okay, so this is the other way around. So again, this is where things can get confusing, right? This is where you earn your bonus, because yeah. Okay, this should work. Let me see. No. Oh. Okay, I'm trying to sum stuff that are different. Let me just check how I did it before. Oh, of course. This is, in all of them, you need to just, yeah. The problem is here. Wait a second. You can't, this is okay. This was okay how it was before. But the problem is that you can't add them. Okay. So let me just copy this little guy here. So you need to select, these are not square. They have one larger side, and this has one larger side on y, and this has one larger side on x. So you can add them. So you need to select only one of the rows, and for the other one, only one of the columns you need to leave out. Okay, this should work. Give me a second. Yeah. And here's the cool thing, I think at least is cool. That it is if you plot this, I'm sorry, this is it's not obvious that how the velocity, this is the acceleration field. So it's actually radial. If you recall, the streamlines were like this. So as you're coming, you have acceleration against the flow, which means the flow is slowing down. And then as you go up, you start accelerating again, right? So this is not obvious at all, I think. Okay, and how you incorporate this in your function? Let me just bring back my function. Is this one? I think. Okay. Once you have that, it should be more or less easy to incorporate. So we're going to incorporate here a x, a y. Then I can write this better. And basically, you just put it here. So dt square half times a I x. Plus, sorry, plus dt square half times ai. And I'm going to call this st2. All right.
Sorry, one
Yes.
question. Isn't necessary to interpolate also acceleration?
Yeah, for sure. You're absolutely right. So we're going to do that. Yeah, here and here, right? We need to say ax equals ax inter of the same thing than here, right? Let me just modify this here. Ay, it should be ay inter, and this should be small a. Yeah, you're right. You're right. Should work, I think. Okay, and now this is what we had before. So let me just copy this whole thing. And let me copy this one. Oh, yeah. So this is what I'm gonna do. We want to test how this compare with the previous one. So we're gonna call this dt, and we're gonna call this 2 and 2 is 2. Now realize, and we're gonna give this. Oh, we have to compute the accelerations. So give me a second. We need to actually do this, right? And this was XR, ER. Okay. Realize that these two are going to be smaller than this. So we can't just use them directly, just as before. So what we're going to do is just use a fraction of them, just as we did before. I mean, leaving out the last row and the last column. So this should work, I think. And then we're going to plot this. And we're going to call this ODT. This is ODT square. And this we're going to plot it on. Okay, I think this is right. Yeah. So they're pretty similar. If we reduce this, are we changing anything? Oh, it doesn't look okay. I think I messed up something. Oh yeah. I'm plotting something wrong here. Okay, so this is it. You can see even with a large delta t, your approximation with the acceleration is better. The black one, you don't have this strange behavior because it's a second order approximation. So maybe with this delta t, there's here they're similar, but here where you have a larger gradient, your acceleration approximation is actually better. In this case, it doesn't really matter much. I mean, the difference is not much in the end. But if you're interested in using as few steps as possible, then the acceleration method is better. Okay, so if you did this, then you got the bonus. Okay, so I think it wasn't that long, and I think it could have been interesting. So hopefully many of you got it right. So I have a couple of minutes for questions about the homework before we take a break. No questions? I see 32 people delivered this homework. That's still not the 50 something that we have in this room. So yeah, I know it's a small, only 5% of the course, but still it's not nice to have a 5% of zero, right? So try to turn in the homeworks, even if you don't do it perfectly or completely. But I think it is important, and I think you can be useful to study. Okay, no questions? Too easy? Too hard? Okay, no comments. I'm gonna upload this to the site, which you can see all the how you call all the templates, all the so you can see what compare with what you did. And when we come back at 5:30, we can start. We're gonna start a new topic. Okay. So if there are no questions, see you in 10 minutes. All right.
Gracias, profe. Nos vemos.
Okay. See ya. Okay. Hopefully you're back. So, antes de seguir, quiero mostrarles brevemente una pequeña cosita. No sé si han visto las noticias, pero hace poco, esta semana o hace un par de semanas, se probó en Venecia el sistema de barreras para impedir que se inunde Venecia. No sé si alguien vio las noticias. Si quieren, ustedes pueden investigar más del tema, pero el sistema se llama MOSE, que es Moisés en italiano, entiendo. Este es el sitio oficial, MOSE Venecia. Pero brevemente les quiero mostrar, brevemente, no sé si quizá algunos de ustedes han estado en Venecia, pero básicamente Venecia es una isla que está adentro de una laguna, que está separada del mar por estas islas de arena. Todas estas islas son de arena. Y Venecia son estos edificios viejos y se está hundiéndose en el terreno. Entonces lo que pasa es que acá en el mar Adriático, cuando hay viento o marejada, el agua es empujada hacia el norte y esa agua entra a la laguna de Venecia por estas tres entradas, estos tres inlets se llaman. Y si eso ocurre durante la marea alta, inunda Venecia. ¿Ya? Entonces estos italianos, en conjunto con varias firmas de ingeniería de toda Europa, diseñaron un sistema para cerrar estas entradas, similar a la barrera que alguna vez conversamos, la barrera en el puerto de Rotterdam. Se los quería mostrar por lo siguiente. Esto funciona, son unas barreras que se levantan, son unas barreras acá. Son unas barreras que están normalmente planas, pero que se les puede inyectar aire. Entonces la barrera está hueca, digamos, es una cuestión de metal a la que se le puede meter aire y la barrera naturalmente flota, entonces puede tener el agua alta afuera. Es interesante. Ustedes, como saben ya de hidrostática, podrían calcular cuánto aire tiene que tener esto para poder levantar la barrera. Esto está hecho de acero. Podrían calcular la fuerza acá. En fin, es interesante. Es medio complicado, encuentro yo, porque acá se ve, son muchas barreras, una al lado de la otra. Entonces hay mucha posibilidad a que esto falle. Pero bueno, esto se probó la semana pasada y más o menos funcionó. Así que puede ser interesante. Ya, se los comento porque me parece interesante y porque ustedes ya tienen como algunas herramientas para poder ver el dimensionamiento de esto. Ok. Okay, let's start with the integral approach. Okay, this is unit 5 in our plan, and basically we just saw the mathematical approach of very, very small infinitesimal volumes, the differential approach, we call this. And now we're going to get into the integral approach, which is basically saying when you evaluate a system as a whole and not only just one particle moving through the system. Okay. So I'm going to try today we're going to see the Reynolds transport theorem, and I'm going to try to cover mass and continuity and momentum equations and see a couple of examples. So you have these slides, you have the book. So I'm going to try to focus a bit on the math, showing how to get to these results. Okay, so basically the idea of this integral approach is that sometimes, actually it's very often, we're interested in what happens with the system as a whole, and not only what happens with a particle of fluid. Okay.
Does this enter to the exam?
Of this Thursday? No.
Okay, thank you.
Hopefully you'll stay nonetheless, because yeah. So for this Thursday, it's only Unit 3 and 4, and Unit 5 and 6 is going to be in the next midterm. And if we have time and we get to see Unit 7, that will be on the exam, which you will be able to skip if you have good grades. So no, this is new stuff. It won't go into this Thursday. Anyway, so we're interested in the fluid as a whole, and not only into a particle. Okay, and here the main idea is that of control volume. Okay, so basically these are two different approaches. One is to analyze the integral approach and analyze the velocity field and how a particle moves, and the integral or system approach has to do more with the control volume. What happens into let's say a fixed region of the space. Okay, it's a bit more Eulerian, but yeah, I wouldn't do the difference between Eulerian and Lagrangian between them. So it's not that's not really very important. Okay, so what we normally do is that it's kind of hard to follow water moving. So what we do is that we define an imaginary uh, volume or region of space which we're going to analyze. If you think on a river, for instance, you're not interested in one particular drop of water, but you think of a reach of the river, let's say a section of the river. So you're interested in what happens, I don't know, in a section, a few kilometers long, and not what happens with each individual drop in it. So in a practical way, we're normally analyzing a specific volume or a specific region, and we call that a control volume. Okay. Now, it is important how you define your control volume. It could be fixed on space, or it could be fixed on. For instance, if you want to analyze an airplane, you're normally going to draw a control volume around your airplane to describe how air flows around it. So in that case, your control volume is actually moving through space, right? So yeah, this is an example. Here you see 3 examples. So you have, let's say you have a pipe, a tube. Your control volume could be just the tube, just what comes in, what goes out. If you have a jet moving, like in a plane, your control volume could be a region around it, and you describe how the air moves around it. If you have a balloon, your control volume could actually be attached to the balloon. So actually the control volume might be changing shape, which is not very common, but you could do. If you have a pool, for instance, your control volume could be just the pool, and you analyze how much water is entering the pool because you're filling in it. But if your pool is broken, then you know that some water is going out, right? So in that case, your control volume is a physical pool. So this is a bit arbitrary, and it's case specific. It will depend on each case, and it is important for you to be smart in how you define your control volume. Sometimes it's very obvious, sometimes it's not so much. Okay. Now we get into the Reynolds transport theorem. This is a theorem. This is a core idea into fluid mechanics. You saw already some of it in Unit 4 in the differential approach. But the main idea is that we can express conservation laws as derivatives of the property that we're interested, and fluxes of the property. We'll see the details. So I'm gonna keep with the slides a bit, and then I'm gonna turn on the blackboard. So basically, the idea is we might be interested in a quantity that we're gonna call B, and this quantity is gonna have a representative quantity per unit mass. You recall we talk about intensive and extensive properties. So let's say we're interested in a quantity B, and this quantity B is just big B, is just proportional to the mass of the fluid by a constant which is small b. Okay, and this is the intensive property. And typical examples of this is if we're considering mass, then your big B is going to be just the mass m, and therefore your little b, your intensive property, is going to be just 1, right? If we are interested in linear momentum, momentum is mass times velocity, so that's big B, and therefore little b is going to be just the velocity. So the velocity is the intensive property of linear momentum. And the same goes with kinetic energy. So it's half mass times velocity square. And in that case, little v is going to be just velocity square half, right? So B is the extensive property we're interested in, and little b is the intensive property, which is proportional to the mass of the fluid, right? I mean, B is independent of the mass, and B is proportional to the amount of mass, okay? And this is important because it's in how we're going to define this theorem. We're going to be actually using B, small b, I mean. Okay, so this is the main idea, and we can do a lot without going into math. So just try to follow. The idea is the following: if you have a control volume, the total amount of whatever property is within the volume B is going to be just the integral of little b over the mass. And since we're talking about fluids, this integral just becomes the integral of b times rho over the volume of your control volume. So the total quantity of whatever property is in your control volume is an integral of the intensive property times rho over the full volume. Okay. So for instance, if we're talking about mass, then B is 1. So the total mass in a pool is going to be the integral of rho over the volume. And since rho is constant, it's just rho times the volume. That's the total mass of water in a pool, right? Now that's the mass at one point on time. But let's say we're interested in how that property changes over time. So the rate of change of the system, by definition, is just the limit of the property inside the system on a time t0 times delta t minus the property in the system at time t0 divided by delta t. So it's just the limit when this delta t is very small. How does it change in a very small time step? This is a definition, and we know that each one of these total properties are going to be the integral of the intensive properties over the volume at that time, right? Okay, now time to switch camera. Hopefully it will work. Okay. Let me just turn off the blur. Yeah. Okay, so is this in the, like always, is this in the right direction? Can you read that?
No, it is inverted.
All right, thanks. Okay, so now try to follow. This is the same that you can see on the slides, but I think it's better if we just explain it. So let's assume you have a certain velocity field described by some by some streamlines. All right, and you have a certain control volume, which I'm going to draw, schematically here. So this is going to be your control volume at time t0. Okay. So we're going to call the property V at time t0 is going to be just the property V on this control volume at time t0. Okay. And now let's assume that sometime later, a small time step, your control volume moves with the flow. Okay. Let me just to keep this on the same nomenclature that before, and we're going to define 3 regions. So the original control volume is made by region 1 and 2, and the new control volume is made by region 2 and 3. Okay. So B at time t0 times delta t is going to be B at 2 plus B at 3. All of these evaluated at time t plus delta t. Okay. And this on t0, this is just the same as B1 plus B2 at t0. Okay. So by definition, the total derivative of V over time in the full system is the limit when delta t goes to 0 of B of t0 times delta t minus B at t0 divided by delta t. Okay, this is a bit cramped. And this by definition is this one minus this one, right? So okay. Okay. So this by definition is just B at 2 plus B at 3 at t0 times delta t minus B, let's just call it CV at t0. Okay. But B2 is just this little guy here is just B at CV minus B1, right? So this is the full property over the control volume minus this area. So if you do that here, you end up with B at your control volume plus B at 3 minus B at 1. All of this at time delta t minus B control volume at time 0. I'm sorry, and this is divided by delta t. This is divided by delta t. You can rearrange this and you end up with B at the control volume at time t0 plus delta t minus B at the control volume at time t0 divided by delta t. So this is 1 plus B at 3 minus B at 1. All of these at t0 plus delta t. I'm sorry, times delta t. Okay. So basically, and this is, all of this has the limit, so I'm just not writing it down, but just keep in mind. Okay, so basically here you can see is the same quantity, but at different times, divided by delta t. So this is actually a derivative. And we know that the total quantity of B is an integral, So you can express this. You can let me write that the B at the t is gonna be, if you take the limit, this is gonna be the derivative with respect to time of the integral over the volume of small b rho the volume. This is this part. And this other part, if you look at this, B1 is the property is this area, is the property in this area, which is entering the control volume, and 1 is actually going out the control volume, right? So this is, you can see it later on, but we will show you, but these are actually the fluxes of the property along the boundaries of your control volume. So this formally can be written down as the flow of B times rho times the velocity projected over the normal, and you integrate this over the area. Okay, and this is the Reynolds transport theorem. It looks more complicated than what it is, but basically what this is saying is that it's saying something very, very intuitive. It's saying the total change of a certain property B is equal to the change of that property within the control volume plus all the fluxes of that property, all the fluxes that are coming in minus all the fluxes that are coming out, right?
Can you say it again, please? So
yes,
the net flux,
the net yeah. So this term is the change within the control volume.
The signal went out.
Yeah. Let's look at the sign because it's not obvious at all.
No,
So,
there is a cut. We have no signal. We don't see nothing.
Oh,
looking for the phone.
Crap. Give me a second.
Okay.
Yeah, I've been having a lot of trouble with VTR today. Can you see it now?
Sí, profe, ahí se.
Yeah, great. Okay, so let me just, this is only useful to explain this. So let me write this down again more clearly. So what this theorem says is the following. It says that the total change of B. Yes.
Profe, entonces el volumen de control pasa a ser el volumen 2.
Yeah, in the previous, I just deleted, but in the previous one is just 3 plus 2. That's the new control volume. I don't particularly like that approach because normally your control volume is going to be fixed. Okay, so normally, give me a second and I will elaborate on that. So
Sí, okay.
the total change is going to be equal to the change within the control volume. So this is B rho the volume over the volume plus the net flux of B rho velocity dot the normal over the area. Okay, so normally you're going to have, let's say, you're going to have a region of space that's going to be your control volume. And you're going to have water flowing through it, for instance. Okay, something like that. Maybe in this case, this is not a very smart selection. So let's say you have streamlines like this. So a smarter selection would be something like this that goes along the streamlines. Okay. Why this is smarter? Because if your control volume is aligned with the streamlines, here you have no flux. Here you have in this side v dot n is 0, right? So you have no flux here. So basically what this is saying is, if this is your control volume and you have water flowing through it, this term tells you how much a certain property changes inside your control volume. Yeah. Normally, if you have steady state, this term is going to be 0 because all derivatives are 0. And therefore, all the change of the property are going to be due to changes in the fluxes. So what's coming in, if what's coming in it's different of what's going out, then you're going to see a change in the property inside your control volume. Okay, so let's go ahead and try to figure this out with mass. Before that, realize the following. Let's say you have here a certain velocity, right? And the normal vector here is pointing in that direction, and here is pointing in that direction, right? These are the normal vector. So here, I'm going to put this in. V dot n, which sign is going to have?
Negative.
This is going to be negative. So everything going in your control volume, this is just a definition, is going to be negative. And in this side, v dot n is going to be positive. Okay, so this integral is really easy to change it. This little guy is going to be very, very similar to the sum of velocities. Well, let me get into this later, but basically you can identify areas, so, or sections. So if this is 1 and this is 2, you can change this for flux 2 minus flux 1 of whatever it is, right? Here you're going to have 0 flux and here 0 flux, right? So the important thing is that the flux going out is going to be positive, so you can also say this, and the flow going in is going to be negative. Okay, and if that's the case, then you're going to have a different than 0 derivative. Okay, so this is convention, but you need to keep it in mind. Okay, going in is negative, going out is positive.
Sir, I'm sorry about the la insistencia, but the first part of the equation I don't very clear.
Yeah. Okay. So that is good that you ask. Let's look at this before. So let's consider mass. If we consider the mass transport, in that case, B is 1, right? So we know that the total mass in a control volume is going to be the integral of rho over dv, right? So this is the total mass, right? Is this clear? I'm going to assume it is. So the total mass inside the control volume is this equation. Therefore, the rate of change inside the control volume is just dm at dt. So d at dt of this expression. In this case, mass is the same as saying just b equals 1, right? So this term is this term, and it represents the change of the property inside the control volume. And what is that clear?
I don't think if I am the only one that is it's a bit sturdy with it, but
Yeah. This is not.
It is like if density varies in the control volume.
No, not necessarily. You can. Let me just.
Maybe an example will get it clear.
This is. Yeah. Okay. Let's say you have a pool. Okay. And you have a hose, una manguera, and you're putting water in it. Okay. We've all done this, right? And let's say, for the sake of the argument, that we can measure this. So what's the mass? At one point in time, the mass inside the pool is going to be just rho times, let's say this is h, times h w l. Let's say that the pool has width w and length l, right? You know this, right? This is just the same as the integral of rho over dv. It's just the same, but in this case, the volume is a parallelepiped. Yeah. But you have to realize that h is actually changing over time, right? So this is the mass at this moment in time. If you come, I don't know, a couple of hours later, then your pool is going to be up until here. This is going to be now h2, let's say. Right?
So the first term is it is not term, but the primer término is the shape change of the control volume. Similar to that.
This one, yeah.
Like the amount of mass contained in the control volume.
Yeah, is how it changes within the control volume. So in this case, your control volume is going to be something like this, right? So this term tells you how it's changing. In this case, we're talking about mass, but can be anything. Can be, I don't know, energy or whatever. How it's changing within the control volume. Okay. And here, so this is just the derivative of the mass. You know this. But here's the cool part of the theorem. I think is the cool part. This is saying that the total change is going to be equal to the change inside the control volume plus the fluxes. Okay. And here's when you need to realize that if we're talking about mass, this guy is always zero by definition, because mass can't change over time in a system. So whatever changes inside the control volume has to be equal and negative to what is coming in to the because of the fluxes of that property. So whatever this comes up in your pool has to be equal to the water that you just poured in, right?
Perfect.
It was actually a nice example of the pool, I think. So basically, if we're talking about mass, let me just simplify this a bit. If we're talking about mass, again, this guy has to be zero. This is just the derivative of rho times the volume of your of whatever water fluid is in here, and this is the fluxes the fluxes along your boundaries. So, and since this is 0, what we can do is we can say, okay, the rate of change is just negative to the flux. So if the volume or the mass inside the system is increasing, that means that remember we said that water coming in was negative, and now we have a negative sign. So we have a lot of water coming in. This makes perfect sense, right? Do realize that this is the velocity of the water, and this is along the area of the surface. Okay, so this was a bit with the hands, right? Not very formal, but the idea is that if you're conserving a certain quantity, then this guy is 0. So whatever is changing inside your control volume has to be balanced by whatever quantity is flowing into or out to of your control volume. Great that you ask questions. It makes it makes it a lot more useful than me just going through the
Sir, are you there?
through the subject.
Profesor,
Hey.
profesor, se le fue la señal a usted.
Yeah, I know. Mi BTR hoy día ha sido un dolor de cabeza, lo siento.
Todos hemos pasado por eso.
Sí. Cierto, no soy solo cierto. Hoy día es muy malo. Okay, so what I was saying is realize that when you have steady state, then the change within your control volume is going to be also 0. So in that case, you end up saying that the total fluxes have to be 0. Okay, so this one, the total fluxes have to be 0. So again, let's say we have the spool, and this is our control volume. And as you pour water in, the level is going up, right? So it's going up until one point where water starts to overflow here. Okay, if you reach a point where this water level is not changing, by definition, the water going out here, which I'm going to call flow, has to be the same water that you're putting in. It has to be the same, right? Because this guy has to be 0, because this is not changing, so this is 0. So all the fluxes and through the boundaries have to be 0. Okay, and that formally that means that rho v dot n over your area has to be 0. Okay, now normally, is that clear for everyone? Normally we can separate this into surfaces. Okay, so what we normally do is we say, okay, so we have this equation, rho v n over dA, and in this case, like in many cases, see that we have one inflow and one outflow. We said that the one coming in is negative, and the one coming out is positive. So we're gonna call F out minus F in. But what is F out? F out is nothing more than the integral of rho velocity that n dA over the area out minus the integral of the same thing or the area in, right? Now we know rho is constant, so we can just pull it out. And we end up with this. And v times the normal, this is just the normal velocity. So let me draw a boundary. Let's say you have this boundary and you have a certain flow. So v times normal gives you this vector, right? So it's the normal velocity. So this term is the normal velocity to that boundary, right? And you can also realize, so let's say you have a certain boundary of your control volume and you have water coming in, for instance. And we're only taking into account the normal velocity. Realize that by definition, the average velocity that comes in has to be equal to the integral of v over dA divided by area, right? So you can see that this integral is the same. The integral of v over dA is just the same as saying the average velocity times the area, right? So if you have steady state and you have one surface over which water is coming in and one surface over which water is going out, so I'm going out now. So F out is going to be nothing more than rho V out, the average velocity out, times the area out. And V in and the flow in is rho V in, the average velocity in, times the area in. And this is 0 by definition. So we have rho at both sides. So what this is saying is that V over area has to be constant. Remember all we did? We said, okay, we're talking about mass, so mass is conserved, and we're talking about steady state. If you have steady state, for mass to be conserved, that means that the velocity times the area has to be constant. We call this flow, or volumetric flow. And if rho is not constant, let's say in a gas, you need to talk about rho v times area has to be constant. And this is called a massic flow or mass flow, right? So you see, when we talk about continuity in the differential approach, we had this differential equation that determined continuity. In our case now, when we're talking about this control volume approach, we have an equation which is not differential anymore. It's a lot more manageable, I think. Basically, this is saying that all the volume of water entering into the pool has to be the same of the volume of water going out of the pool. Okay, and that makes perfect sense. I think it's pretty intuitive. Any questions? Nobody. Before we take a break, I want to show you something. Do you recall in the homework we had the following velocity profile? Yeah, it was like that. Wait a second. Any of you have it at hand?
Yes, it was that. It was that.
It was that? All right. Thank you. And you recall, probably, this looked something like that, right? Or something like that. Sorry, my drawing is not as pretty, but you know, you get the feeling. And we said, okay, let's take point 3,1, this point here. So 3,1. Now, this is a typical question. What's the flow, the volumetric flow going in? You should be able to answer this kind of stuff. Okay. I have a nope. Nope what, Matthias? It wasn't this equation? Okay, let's integrate this. So Q, the volumetric flow, is going to be equal to the integral. Since we don't mind about rho, about density, because density is constant, we can take it out. So it's going to be V times the normal over the area. And let's just assume, a 1 meter width of this flow. This is a horizontal flow, right? So V times normal, that's just the horizontal velocity, right? And we said if it's going in, then it's negative, right? So this is going to be just the integral of U over this area, and the integral, and we said U is minus x. This is right. It's minus, yeah. It's minus 6x over the area, right? This is going in, so it's negative. This is right. Okay, so this is evaluated at 3, so this is just 6 times 3, and this area is just 1. I'm sorry, this is 3. So this is just 18. 18 what? Well, this is velocity. In this case, this is velocity, this is area, but we're missing 1, so this is meter square seconds, right? And so along this between the axis and the point of interest, we have 18 minus. We have 18 meters squared per second of water coming in.
There isn't meters elevado a 3 cúbico.
Yeah, but yeah. If we assume this has 1 meter width, going up, then yes. But we can also talk about, spatial. I mean, we've done this before. We can only just consider this plane, right? So we could do that. But yeah, just if you're consistent with this, we're integrating dA between 0 and 1. So yeah, could be just if you consider this has 1 meter depth, in the vertical. Otherwise, it's squared. It's not very important in this case. And the point is that this reach up until 3. Do you know what this point would be? By symmetry, this has to be 1, right? So the streamline that we drew in the homework, we could use this streamline to define a control volume. Could be a very, very useful definition. And you see all the water that is coming into our control volume is the same water that's going out. You could compute it, but by symmetry it's really easy to show that this flow has to be the same going in. Plus, you can anticipate that by this theorem. So maybe you can work that out on your own and compute the flow going out. It should give you the very same 18. Okay, any questions before we take a break? Okay, so let's take 10 minutes break. And at 6:30, I know it's late. I know you have another exam. I'm sorry, but there is one thing that we need to address by the end of the class. So I'm going to try to make it short. So let's see you at 6:30, and then we'll try to take just 20 minutes or half an hour. Okay? Okay, see you in 10 minutes.
See ya.
Okay, let's move on. Thank you all 15 for being here yet. Let's now see transfer of momentum. Okay, we talk about mass, conservation of mass just now. Now let's talk about conservation of momentum. If we're talking about momentum, then the property we're interested in is mass times velocity, right? And therefore, little b, or the intensive property, is just the velocity. So what the Reynolds transport theorem says is that the total derivative of the linear momentum is going to be equal to the change of momentum inside the control volume plus the net fluxes of momentum through the boundaries of the control volume, right? So the same as before. Now, if we assume that we have steady state, which is a very reasonable assumption, or is a very common assumption, then this is going to be 0, right? And you know from physics, what is the derivative of the momentum? You should know that, right? The time derivative of momentum. No one?
¿La aceleración?
No. Okay, but
La velocidad angular.
no. Okay, let's take a moment here. So dm at dt, if the mass is constant, then this is just m dv at dt, and this is m times acceleration, right? And what is this?
Fuerza.
Forces. Excellent. So this is the general principle. Newton said that it was actually, he was talking about momentum, really, not ma. So really, when you say F equals ma, it's really F is mv prime. All right. Okay, but that's just, you should know that. So this is really the sum of forces. The sum of forces are going to be equal to the change of momentum within the system, which is normally 0, plus the sum, the integral of flux of momentum. Okay? And this is really cool, I think. So basically, you all done this, that you have a hose, una manguera, and you turn it on, and the hose moves, right? It is moving because the water has momentum, and the momentum is changing how it enters and goes out of the hose, and it's creating a force. Okay? So this integral, again, let's talk about this very control volume that we had before. We know that the velocity in is 18 meters per second, and we know it's the same velocity out, the average velocity, and we know that the flow is just this velocity times 1. This is just 1. So 18 meters square or meter cube per second. So let's talk about this section 1 and section 2. You know that through these boundaries, there are no fluxes because they are just parallel to the flow. So the sum of forces are going to be equal to, let me just take a long way. V rho V n dA over 2 minus the same integral over 1. V rho V n dA. Okay? Now, how can we solve this? In this case, it's not the same as before, in which we said, okay, the definition of mean velocity was very useful. So now what we can do is we can cheat a bit. So we can say okay, this part of the integral looks pretty similar to what we did before, right? So instead of integrating all the velocity, let's replace that with the average velocity. So let's take the average velocity and then this integral. And this integral we saw before, this is just rho average velocity, I'm sorry, times area, right? And we call this Q, right? So we can approximate this. Do you see this? So you can approximate this to the average velocity times Q, or actually times rho Q, right? This is Q. So we can approximate this. I'm gonna delete this. So we can approximate this to V2. The typical form is like this: rho V2 Q minus rho V1 Q. So the sum of forces has to be this. And I think this is a really cool equation and a really useful one. Now, keep in mind that this is a vectorial equation. So the forces have direction, and these velocities also have direction, right? Also, in practice, I mean, this is really practical. But if you want to be like more like a more rigorous approach, you would amplify this by a factor beta, which is a Boussinesq coefficient. So beta is nothing more than a correction coefficient, because it's not really true that you can approximate the velocity here to the average velocity. That's only going to be true under some cases. So beta is the actual integral of b squared over the area divided by VQ. Okay, this is not very, very important, but beta is going to be in the range of between 1 and, let's say, 1.3, depending on how far away from the uniform your profile is. In our case here, the velocity is uniform in the section, the normal velocity, mind. The normal velocity is uniform. So in our case, beta is just 1. For all practical computations, you can just forget about it. Okay. Now, if this equation is clear, is it clear to you? So basically, what the Reynolds transport theorem for momentum is saying is that the force that the flow is exerting is just related to the momentum entering and going out of the control volume. Okay. So we could compute the force that the water is doing into this control volume using this equation. Now, intuitively, where do you think this is going to force to create a force? Basically, if you have a piece of metal with this shape and you put water in it, and the water bends this way, where do you think the piece of metal is going to move? Can you see it?
It'll move to the left and down, maybe.
To the left and down, right? Yeah, that's right. Because you have, yeah, this is vectorial. So this term is acting on the y, on the j, and this one is acting on the y, right? So if we don't have any other forces, this term here, mind you, this represents all the forces acting on the fluid, the body weight, the pressure forces, all the forces, right? In this case, this is a planar flow, so we don't have any of those. So all of the forces are due to the hydrodynamics. So what this is saying is this is already the reaction force. Okay, so the reaction forces have to be equal to these values, right? So these are just directly the reaction forces. I might be wrong with the sign, so let me just have a look of this later. But already these are the reaction. These should be the reaction forces. So it should be a force in that direction and force in that direction. But I think this should be in the other one. So let me have a look at this, and I'll have it more clear for you next Monday. Also, we're just so few now that it doesn't make sense to keep on going. Okay, so this was for today. We're gonna finish this section probably next Monday or the one after. So before we go, any questions of what we saw today, or any questions for the exam? I mean the midterm of Thursday. Solo como consejo, ustedes tienen, hemos hecho varios ejercicios, tienen los ejercicios del libro disponibles para revisar, tienen las respuestas, me refiero. Alguien me preguntó si estaba el libro físico disponible, no lo sé, entiendo que sí, pero me da la impresión que no es muy fácil de encontrar, así que les recomiendo leer el libro en PDF, desde Canvas. Pero eso, revisen las cosas que hemos hecho en clase, revisen las cosas que hemos hecho en las ayudantías, y debiera ser más o menos simple la prueba del jueves. Ok, ¿alguna pregunta? Parece que no. Si no hay nada, nos vemos el jueves a las 7:30, me parece que es. Revisen sus calendarios. Eso, y buena suerte.
Nos vemos, profe.
Chao, chao.
Chao, profe, gracias.
A usted.